Let's take a quick look at Euler's method here, which is a way to approximate values of a function without actually knowing the function, just knowing the differential equation. So Euler's method, if you recall, the differential equations describe the slope at every individual point in space. And so functions can be approximated using these differential equations by assuming, or by using that derivative and assuming that the function is close to linear at a given point. And then if you want to approximate the function based on the differential equation, you repeat these linear approximations. Now, what does that actually look like or mean? If we take a look here, we've got an example of a function, one of x. I've got the tangent line to that function. So this was solved using the derivative, finding the derivative. That let us calculate the 1/4 here. And then we knew the point 2 1/2, and that let us find the other things for the equation. Now, if we zoom in really close to 2, we see that for 2.1, the value of the tangent line at x equals 2, and the value of the actual function, these are quite close here. So the graph of the function on the tangent line, if you look, they basically look linear, because the tangent line, of course, is linear, and the function line, and anytime you zoom in close enough, a continuous function will look linear. And so this means for, say, 2.1, if I knew the 2 and 1/2 was one pair of numbers, I could find the slope, calculate the tangent line, plug in 2.1, and I get a number of 0.475, which is quite close to the actual value. So looking at an example, if I have a differential equation, say the function d by, let me see what it was in your notes, dy by dx is equal to 2x minus 3. And I'm starting at y0 equals 3. And I want to find what y of 2 is equal to. Well, I can just do this by saying we start at the point 0, 3. Then we're going to approximate the slope of that point. dy by dx is equal to 2 times 0 minus 3, which is equal to -3. Then if I know that for a linear line, the change in y over the change in x is equal to the slope, which is -3 in this case, and I know that I want to use step sizes, I want to change my delta x by 0.5, that's what this means here. Well, then I can say that I know that my change in y will be -3 times 0.5, which is -1.5. So this gives me a new point of 0, -1.5. Of 0.5, because I have to change my x and my y value, because if I step to the side by x of 0.5, now I step to the side for y of -1.5. The slope is now going to equal -2, and you can check the guided notes for all the steps kind of worked out. If the slope is -2, delta y is going to equal -1. That gives me a new point of 1 and -0.5. Or sorry, -1, which would mean, sorry, that should have been +1.5. 3 minus 1.5 gives 1.5. 1.5 minus 1 gives 0.5. Then we've got a slope of, I believe it's -1. Yeah. -1, which means a delta y of -0.5. That gives us 1.5 and, sorry, this is sloppy, 0. Then we've got dy dx the new slope at this point is going to be 0, and that means my change in y is also going to be 0. And that means when I get to 2, my y value will be approximately 0. So let's look at how accurate this is. Well, you can see in this case, I graphed the particular solution we were looking at in blue, and then the orange or the red line represents kind of the approximations based off of 3. So you can see at first it is quite accurate, even with a big step size. But as time goes on, they become less and less accurate typically. Usually not so bad that it's unusable, but as time goes on, you do lose accuracy with these kind of linear approximations. So that's Euler's method. As a formal definition, if you're given an initial value problem of, say, y equals f of x, y of x naught equals y naught, to approximate, you're going to say that the nth x value is equal to x sub 0 plus n times h, where h is the step size. And the nth y value is going to equal the n minus 1 y value, so the previous y value, plus h times f of x to the n minus 1 y of the n minus 1. This is also equal to delta x, by the way, if you prefer thinking about it in terms of that. Basically, all this is saying is every time you move a little bit to the left of x, and then you use the previous values to get a slope, and you integrate this should be f prime. You use the previous point, find a new slope, multiply by delta x, add it to the previous y value. Repeat, repeat, repeat. So the process here, start at the initial position, solve the differential equation to find the slope, or not solve the differential equation, plug in the initial position to find the slope of the initial slope at the initial position, calculate the change in the dependent variable, so that's the y value, and again that's going to be delta x times slope. Estimate the next point, so that's going to be x plus delta x, comma y plus delta y, and then repeat. Instead of being at the initial position, now you're going to be at x plus delta x, y plus delta y. So solve for the slope, calculate the change in the dependent variable, the y, by doing x delta x times slope. Add those to your values and continue. We'll do an example here. I'll do it in another video because this one's getting a little long and you can kind of then refer back to it later.